Hello and welcome to this lesson video where we will learn about how to prepare mass diagrams, derive um, uh, earth moving planning insights from them, and use them to identify, balance, cut to fill operation zones. The video covers the shown two learning objectives. Mass diagrams are very useful in linear earth-moving projects like roadways and airstrips, where the dimensions along the project profile are much longer than those in its cross-section view. Mass diagrams with the help of profile views can help the project managers to visualize better the earth-moving scope and plan more efficient cut-to-fill CTF operations. Although mass diagrams are specific to linear projects, but its balancing principles and methodology can still apply to other types of mass and structural excavations. Specifically, mass diagrams can be useful in finding the shown planning parameters. A single mass diagram can help in calculating the cut and fill quantities over the project profile. Based on that, we can use the project's mass diagram to visualize the number and boundaries of the CTF operations. For example, CTF operation for an example CTF operation, this row profile shows one cut and two fill areas. Mass diagrams will help in deciding to move the excavated soil from the cut area to the left area or to the right area. For each identified CTF operation, the mass diagram will help calculating the average hole lengths and grades of the earth-moving equipment. This information is critical to match the different earth-moving equipment, like dozers, scrapers, and trucks, to their appropriate hole distances to end up with an economical operation. Finally, mass diagrams can be helpful in answering a very critical question. Will the project require additional soil to be hauled to the site, or there is a lot of excavated soil that needs to be hauled off the site? Hauling soil to and off the site is costly, and having a clear understanding of such long distance haul quantities is critical to produce quality bid estimates. Before we can use mass diagrams, we'll have to first make them. Mass diagrams are prepared and developed through a long process of table calculations, as shown in this completed one. To prepare a mass diagram table, you will need the end areas of both cut and fill at each station, and also the topsoil stripping between each successive pairs of stations. Let's see the coming slides how mass diagrams are prepared. The first step is to calculate the cut and fill volumes between each pair of successive stations using the end area calculations. As you can see in this cross-section view, you can have both cut and fill areas in the single station, like in the fifth station, 2 plus 50. Also, from the last lesson, we'll have to skip the first volume calculation for the first station, as we need two stations for the end area calculation. The first end area calculation will be applied for the cut and fill volumes between station 1 and 2. The fill volume is calculated as the average of both fill and area. Fill end area 0 and 115 square feet times the length between the two stations, 50 feet. So we end up with 106 bank cubic yards for the first volume. The first cut volume equals 0 because both stations 1 and 2 have 0 cut in areas. You continue applying the end area calculations for the rest of the station successive pairs. Please notice that we are using so far two different units for the cut and fill volume. We are using bank cubic yards for the cut volume and compacted cubic yards for the cut volume and cubic yards for the fill volume. Remember, the dimensions of the cut area are for the soil in its natural bank state, while the dimensions of the fill area of the section are of the soil after it is compacted. The second step is to revise the cut and fill volumes we just calculated to account for the need for stripping the topsoil in the site. Topsoil is a natural organic surface material, usually up to 3 feet deep from the natural surface grade. This topsoil typically has no good use in construction to build embankments or backfills, so they are disposed in outside dump sites unless the project calls for reusing them to maintain the site natural vegetation as part of the final project. From the geotechnical report and the cross-section views, the topsoil stripping volume is provided for both the cut and fill part of each station segment. The topsoil stripping volume is calculated based on the footprint of the cut and fill areas from the layout view times the stripping depth as recommended by the geotechnical soil report. Now, how these topsoil volumes should affect the cut and fill volumes we calculated from the previous step. To understand the topsoil impact, we need to follow the cut and fill sequence and acknowledge that their depth is provided based on the natural surface grade, which is the surface of the topsoil. For a fill section, the contractor cannot fill on top of the topsoil because the topsoil lacks the structural strength to provide strong embankment and subbase for the road or taxiway. So the contractor will have to strip the topsoil first, fill this void that was just stripped, and then fill the actual embankment that is shown in the section view. As such, we are filling more than we initially thought. So we end up with adding the stripping volume below the fill area to the fill volume we calculated in the previous step. On the other hand, the cut area will be stripped first to get off the no-use topsoil before cutting the good soil that can be reused to fill the other areas of the project. So initially, our initially calculated cut volumes need to be reduced by the topsoil stripping volumes on top of the related cut areas. To summarize, topsoil complicated CTF operations for the contractor because it reduces the soil cut material that can be available for fill, and it also increases the fill volumes to compensate for the stripping void left behind the topsoil. So we expand the table with two more columns. In column 8, we update the cut volume by deducting the stripping done at the cut part of the segment. For example, for segment between stations 5 and 6, we deduct 26 bank cubic yards from the cut volume, and we end up with the revised volume of 144 bank cubic yards. On the other hand, the fill volumes are revised in column 9 by adding the stripping at the fill segment to the fill volume list in column 5. For example, the fill volume of the first segment between stations 1 and 2 is increased from 106 to 124 by adding the stripping fill value in column 7. The next step is where we bring the cut and fill volumes to an apple-to-apple values. Remember that we are preparing this mass diagram to be able to balance the cut and fill volumes, which we cannot do if they have different measurement units. So we are transferring the fill quantities from compacted cubic yards to bank cubic yards by dividing over the complement of the shrinkage percentage value. Please refer to the previous lesson where we covered the soil properties to review the soil transformation between bank and compacted states. Almost there. The next step is to get the algebraic sum of the cut and fill quantities of each segment by subtracting the fill volume from the cut volume. As such, we consider cut volumes positive and fill volumes negative. And finally, we calculate the mass ordinate at each station of end of each segment. The mass ordinate is another name for cumulative sum, where we add up the cut fill volume algebraic sums from the start to the end of the project. By this, the mass ordinate will give us a good idea about the cut fill balance from the beginning of the project to any point along its length. If the mass ordinate is negative, this means that there is more fill than cut up to this point of the project. Now we can plot the mass ordinate to have the mass diagram. The mass ordinate is shown on the vertical axis, and the project length or stations as shown along the horizontal axis. I'm showing here a profile view and its corresponding mass diagram, which both provide a full story of the cut and fill work. Starting from the left, the profile shows cut segment from point A to B, and then a fill segment from point B to C. You can see that the mass diagram is ascending in the cut segment and then flattening at the point where the profile and natural grade intersect, and then descending in the fill segment. This is because we add the cut volumes to the mass ordinate and deducting the fill volumes from the mass ordinate, as shown in the mass diagram table calculation. Now we can visualize the balanced CTF zones where the cut volume is sufficient to balance the fill volume. We identify the balanced zone by drawing a horizontal line along the mass diagram and crossing it in 2 points. The balanced line we draw here visualizes a CTF hole operation that's moving the dirt from the left cut segment to the right fill segment, while knowing the start and end points of the balanced zone, meaning point A and point C. Now we can visualize the balanced CTF zones where the cut volume is sufficient to balance the fill volume. And the CTF operation is balanced because the whole quantity Q, as the height of the mass diagram, contained by the balance line, equals the soil cut volume and is used for the fill volume. Interestingly, we can split a balance zone into smaller subzones by drawing more balance line. Each balanced subzone will represent a separate CTF operation with a different equipment, like we see in the next lesson. On the screen, we created 2 balanced CTF operations by drawing 2 balanced lines through the mass diagram. The whole quantity of each CTF operation equals the mass ordinate delta contained between the mass diagram and the relevant balance lines. For the first CTF operation, the whole quantity is between the mass ordinates at point B and the points of the first balance line, points E and points F. The quantity of the second CTF operation is the mass ordinate difference between the mass diagram intersects of the 2 balance lines. The first whole quantity is cut from segment EB, hold, and then filled in segment BF. The second whole quantity is cut from segments AE, hold for a longer distance, and filled in segment FC. This is another example where you can see two balanced CTF zones in their all directions. But we can see here that there is a last segment of the project that was not included in any of the balanced zones. That one between points E and F. From the profile view, this is a cut segment, but the resulting soil has no place to be used as a fill. So this soil material has no use on the site and needs to be hauled off the site. This is why we call this project a waste project, because we are wasting an excavated soil instead of recycling it within the project, which is not feasible with the project design geometry. As a hint, you can identify a waste project by finding a positive mass ordinate value at its ending station. This is another example with 4 balanced CTF zones, but we see now a case of a borrow project. We can know that by seeing a fill segment that is not part of any balanced zone, and the negative mass ordinate at the ending station of the project. For a borrow project, the contractor will have to buy dirt and haul it to the site for this unbalanced fill segment of the project. This is the end of this video, where you learn about the mass diagrams, their preparation, and their use to identify balanced cut-to-fill operations. In the next lessons, we will see how to use mass diagrams to prepare more detailed CTF operation plans by specifying their appropriate equipment and their whole operation attributes.